All right. Last talk of the day. Mario, are you giving the last talk of the day?
Yes.
Mario is giving the last talk of the day. Go for it, Mario.
Sorry.
I hope that's not on camera.
So, I'm going to follow the same line that the guys have been following today, and specifically quantitative information flow. But the focus is going to be the problem that Miguel highlighted in the end of his talk. There is interactive systems. So far, they have presented a scenario where you have like secrets and observables, and then your system takes some secret, does the computation, and then produces the observable. And it's the case that in several applications in real life, it's not so simple. You can have like secrets, computation, observables, then you have some secrets being fed to the system, more computation, observables, and so on. So one simple example is that if you have a website that can sell stuff, very simple website, and suppose you have only two products, a cheap product, an expensive one, and then depending on the product offered, you have two possible buyers, a poor guy and a rich guy. So in this example here, we have some probabilities assigned. So the seller is going to offer cheap or expensive probabilities R and the inverse, 1 minus R. And also, depending on the product offer, the poor guy might buy with some probability, but the product offered is an expensive one. The probabilities might change. So the thing is, we consider that the offers are observable, so everyone that has access to a website can see what's being offered, but the identity of the buyer should be kept secret, so we don't want to disclose it. But the problem in this protocol here, in this very simple example, is that the observables occur before the secrets. So when it happens, if you try to use the classical definition that we've been using during this whole day of channels as calculating the conditional probability of observable given secret as the joint probability of the traces with that has this observable and secret divided by the secret, we arrive to a situation where the channel metric is not constant. For instance, in this example here, if you try to build the channel matrix, so here we have the secrets, and it's going to be the poor guy or the rich guy, and observables, cheap or expensive. And we apply this formula, what we get is a matrix. I'm going to use RQ1 plus RQ2. And we can proceed with the math here. But right away, what we can see is that this probability here is not constant anymore with relation with the input distribution, the distribution of secrets. So if you change the distribution of secrets, in general, for every different distribution of secrets, we're going to have a different channel matrix. And if you have a different channel matrix, we are going to have for different distributions on secrets, we are going to have different mutual information, and worse, we are going to have different channel matrices. The channel matrices are going to be different. So capacity that is defined as the maximum mutual information over all possible input distributions doesn't make sense anymore, because every time we change the input distribution, we get a new matrix. So we cannot fix the matrix and maximize over the input distribution. So that's the problem that was observed in the paper that Miguel presented earlier. So we tried to fix it. So what we did is that we stopped using this very simple model of channel. Because what happens here, these channels are discrete memory-less channels. So they don't have any memory. Every time you feed a secret, it generates an observable with a probability distribution that is fixed. It doesn't depend on what happened before. And moreover, there is the implicit assumption that there is no feedback. So when the system produces an observable, this observable has no influence in the future secrets. So when you look at a protocol like this, you see that it's not exactly the case. When you have an observable, chip for instance, it indeed has an influence on what is going to be the distribution of secrets. So we thought, well, maybe it can be captured by feedback, and that's what we proposed to do. So we moved from the classic channels without memoryless, without feedback, to channels with memory and feedback. So the idea of memory is that the channel is going to be able to keep a state of computation, and the probabilities can evolve according to the state of the computation. And feedback means that the system can be interactive in the sense that observables can influence secrets that are going to generate another state of computation that can influence the secrets again, and so on. So the general idea is that we have, as usual, our channel, and in this presentation we are going to name secrets that are the same as inputs by A, and observables that are the outputs by B. And it works exactly the same, with the difference that once an output is produced, it has a delay of time 1. I'm going to be more precise about this when you're formalizing. But the secrets can be influenced by the outputs. The model of channels with, general channels, and specifically also channels with feedback, come from communication theory. And the idea is that feedback can make it much easier to encode the message. It's an interesting result that in memoryless channels, if you have feedback, your capacity does not increase. If you have feedback or don't have feedback, the channel has the same capacity. However, if you add feedback, the encoding scheme can become much, much simpler. So, just an example of how feedback can help in this sort of situation. Suppose that we have what is known as the binary erasing channel. So, we have 3 possibilities, 0, 1. We're transmitting a bit. And the bits can be transmitted with success, probability P, for instance, but it can happen that the bit is erased with probability 1 minus P. In this specific binary eraser channel, when a bit is erased, the receiver knows it. So there is a special symbol, E, that says it was erased. You know that this fail happened. So it's easy to prove that the capacity of this channel is P, because in every transmission you have a probability P of success. So if you take the use is going to infinity, you have P bits transmitted per use. But how do I achieve it? With feedback it's very easy. You transmit a bit. You put 0 here and see what you get here. If you get 0, move to the next bit. If you got erased, it was erased, you just retransmit the bit again until you're sure that it passed through the channel. So since you have access to what is being seen on the other side of the channel, you can improve your encoding and make it much, much easier. So that's the motivation of feedback for communication. It's not exactly what we're looking for, but it happens that it's going to be very, very useful for us. So one interesting thing too is that something that Massey observed in 1999 is that when you have a channel, we have motor information. There is the amount of information that you have from B by observing A or vice versa. Motor information is symmetric. The amount of information that you can get from inputs by observing outputs is the same as the amount of information you can get from outputs by observing inputs. But when you add feedback to the channel, Massey observed that this motor information here can be indeed split in two senses. You have what is called directed information. And directed information is the information that goes through the channel from A to B. And there is another flow of information. That is the flow of information that goes from B to A through feedback. And what's really interesting is that motor information is the sum of information in both senses. We are going to show it exactly like with more detail in a bit. But what's really interesting is that the directed information represented like this also you have the information from outputs to inputs, and Massey showed that is equal to the motor information. What is capacity in a channel with feedback? If you maximize overall input distributions of motor information, we were considering that the feedback here also contributes to the channel capacity. And it's not exactly the case, because what we're trying to maximize is the information flowing through the channel. The feedback increases the correlation between the two random variables, but it's not useful information in the sense that it's not helping to deduce A from B, B from A. So we need to separate that. And it's going to turn out too that in interactive systems, this guy is going to play an important role as the definition of leakage instead of this guy. But it's just an overview of what we are going to talk about today and a bit of motivation coming from communication theory. So, okay. So, we are going to use channels with memory and feedback to model interactive protocols or systems. And we're going to use, as a model of attacker, the channel entropy as defined by Koff and Basing. That is the sense that our attacker can make questions of the sort, is the secret equal belongs to a set S? So the attacker can do this kind of question, and it's measured by channel entropy, channel motor information.
Can I ask you something? If you're going to be allowed to use feedback in these channels, is your mutual information per unit time? Are you measuring it after unit time?
Yeah. Yeah, we are going to use the channel several times, and then take the motor information over the whole execution of the...
So then when you write I of AB, what you really mean is mutual information divided by expected time?
Oh, yeah, I'm going to go through there. Indeed, we're going to have a sequence of until time t. Indeed, we have AT is equal A1, A2, until AT uses of the channel. So we have a string being used over and over and over and over, symbol by symbol.
Are you going to amortize it over time, or you just need to assume you're extending a sequence?
It amortizes, yes. No. The whole sequence, no, because the formula, when you apply the formula of Peticonda, yes. Here? Yeah. 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 That's true. No, it's the whole sequence. No. 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 The capacity is divided by T, but not the information. That was missing capacity. So, back here. So, yeah, it comes to talking about this sequence here, it's good to introduce the notation that we're going to use. So, as I said, A is going to stand for input, B for output, and the channel is going to be used in a sequence of execution, so execution computation. So we are going to represent with Greek letters the symbol that is produced, the input at every time t. And if we're referring to a sequence of t symbols, we just put it upper script. And the same for outputs. We're going to represent like this. So we are going to assume too that there is a maximum time t, big T, and the channel has a finite horizon. So we are going to use up to t times. There is no infinite execution of the system. Okay, so coming back to when you have two random variables, we don't need to think about channels, but we can think about channels if you want. The joint behavior, if I'm going to use the channel t times, big T times, the behavior of the channel is completely described by the joint distribution of the input and output sequence. So if I have the joint distribution of alpha t and beta t, I have the whole behavior of the system. But if you apply the chain rules of probabilities, it can be shown that this guy can be written like this. The product for every time step of the probability of an input symbol given the history so far times the probability of the output symbol given the history so far. And what is important in this formula is that to fully describe the behavior of the system, it's enough to describe how to produce an input given the history so far, all the previous inputs, all the previous outputs, and how to produce an output given the history. And note that here we have t instead of t minus 1, because to produce an output, the input symbol is already available. So we have a bit more of information. And if we write this formula like this term represents memory in the sense that the input, this term down here represents memory. Sorry. In the sense that an output can depend on the whole previous history, and these terms here represents feedback, because an input symbol can depend on output symbols. So the generation of new inputs is going to depend on the outputs, and it's exactly what we want. What's interesting too to notice is that if you restrict this guy here to depend only on previous inputs, and if you restrict this guy here to depend only on the current input, that's exactly what is discrete memoryless channel without feedback. So the channel without feedback and memoryless is a special case of this general behavior here. And if we plug these two guys here, we get the classical equation of channels without memory and feedback. That is just the product of every use of the channel, the probability of producing B given A every time I use it. So this is not another different type of channel. It's just an extension of the classical channels with memory and feedback. Without memory and feedback, we just extend it to the case where we can have these possible increments. it becomes richer. So, okay, so there is a this idea of memory feedback phase of something that has been in literature for some time. Massey was the first one to propose directed information in 1990, and then Gray in 1991 conjectured what would be capacity in channels that had feedback, and he made a conjecture, but he couldn't prove it back then. But 2 years ago, in 2009, Tachikoda and Mitter they came out with a very interesting result. They published a paper where they could model channels with memory and feedback in a very, very nice framework and provide a formula of capacity for these channels. It was the first time it was done. And then it was very good for us because we were looking for exactly for it. So the model they have is a bit more complicated than the one that I wrote, but I will write it down here and I will try not to be too technical and give the intuition behind it. But basically, we start with your channel, and you have the probability of producing an output given the history so far. So this input comes from somewhere and an output is produced. The thing is that these guys will make explicit the presence of an encoder. An encoder is a guy that is gonna produce an input symbol according to a certain function that takes feedback into account. So there is an encoder here. It uses a function that depends on time. So it looks at the feedback and produces a new input symbol. So of course, there's a delay here. The feedback needs to be provided. And the thing is that what these guys were really smart in doing is that they looked at this feedback channel, and the problem with the time capacity is that the channel metric is not invariant. So what they did, they defined this whole thing here as a black box, and another channel that has here whole functions. So So now what we have is a channel that instead of giving an input symbol, it gives a function that is going to be able to produce the input symbol given the feedback. So now this outermost channel here is a channel from functions to symbols. Internally to the channel, the input symbols here are produced taking the function, take the feedback, produce a new symbol, and it's done internally here. But the channel itself, this outermost channel, doesn't have feedback. And then we are able to calculate the capacity on this outermost channel. The trick is how to make these functions here behave in a probabilistic equivalent way to the probabilistic behavior of this alpha here. And we are going to do that too. So, but what is important in this model here is that at the beginning of the computation, at the first step, code functions are chosen, and at each time, the function is given to the channel. So, the channel, just here there is a deterministic calculation, it's a function. Take a look at the feedback, produce the symbol, send the symbol to the channel produces an output, the output goes out. So here, there is a delay in the feedback, the sequence of outputs is updated, and then the encoder can take another function, calculate it again, and it goes on. And then what the decoder and meter were able to prove and to define, they took again the concept of multi-information of massive. So here we have the direct information that flows from the whole sequence of inputs, the whole sequence of outputs. So the channel is using T times. It's the sum of the mutual information that is available at each time. So the idea here is the following. The information that flows from A to B is the sum of the mutual information of the past history of inputs and the current output. So what's going on here? I'm worried only about the information that is correlated to B up to the time T. I'm not looking forward in time. If instead of a small t here, I had a big T, then this guy would be exactly motor information. So the difference between motor information and directed information is that I'm not allowed to look forward in time while producing a new symbol. If I'm taking into consideration direction, I have to restrict the formula to what is available at the moment I'm looking at the system. Equivalently, the information flowing in the other sense is defined similarly, with the difference that when I'm producing a symbol AT, I have available to me only the outputs until time t minus 1, not t. And those two guys, if I sum those two guys, I get exactly the mutual information between them. And then they were able to define what is capacity. And then the capacity is amortized over the amount of channel. A capacity of channel that can be used T times. If you can use it like infinite times, you take the limit, but you're not going to use it here. So that's the framework we're going to use. And we're going to model our protocols, going back to the protocols we're modeling, as interactive information hierarchy systems. So the idea is that I'll write an example here on this part, and I'm going to go back to it several times. So first, we put every protocol we have in a normalized form, and it without loss of generalization, because we can show that it can always be done. So, at the first step, you always need a secret. Then you can have observable, so going back. So suppose you have a system that is going to a website that sells products. So first, you offer a cheap or expensive product. So depending on what was offered, you have a probability of the poor guy buying or the rich guy buying, and then the seller can offer something else, cheap or expensive, and then another guy can buy, and so on. So model every protocol in a tree like this with some properties. First, that we are going always to alternate between levels, secrets and observables. So in one level we can have only secrets. Then in the following level, only observables. Then only secrets, then only observables. Also, you always start with a secret that always ends up with an observable, just to make the keys here compatible.
These properties are not restricted, right?
No, they're not
So you
restricted.
can start with something general and you transform
Yeah.
it into something useful.
Yeah, every interactive system can be modeled like this without loss of generalization. You can do a transformation that writes the equivalent tree before. Yeah. It depends on indeed on the. Yeah, so we're going to talk about now. We assume in our protocol that observables are always probabilistic, so we always have probabilities assigned to observables. It's the behavior of the protocol. And the secrets, the inputs like poor and rich, it can be either probabilistic. In that case, we call this a fully probabilistic system. Or if you want to abstract from the input distribution, we can assume that they're non-deterministic, and then we have what we call a secret non-deterministic system, because the secrets are non-deterministic. So that's what you meant.
And the can they be probabilistic in some places and some other non-deterministic? Because you have many selection of secrets now.
Yeah.
So the code function is the one solving that non-determinism?
Yes. Yeah. I'm going to talk about.
So you can have smart non-determinism too.
Yeah.
As long as it's on the secrets.
Yeah. The observables need always to be probabilistic. It's the behavior of the protocol itself. And then we have predominant inputs. We can assign probability distributions, or we can say it's non-deterministic. And then the non-determinism is solved by the code functions here. A code function decides what's going to be the next input symbol
In each step.
in each step. It's like a scheduler, exactly. So we're going to deal with two main cases. I mean, you can also have some secrets that are non-deterministic and some secrets that are probabilistic, because you can have like more than one input distribution, but they're going to be deltas of direct. So yeah, it's kind of detailed, but it can be done.
But when you were talking about this Tatikada meter, you said that the encoding function, that was a function.
Yeah, it's a function, it's deterministic.
It's deterministic.
Yes.
But now you say in your framework it's not.
No, but we are going to make this fit into this, and then that's exactly the main result of the.
So what you take the worst possible choice
No,
among
so
all
basically
the.
the channel is going to encode the probabilistic behavior of the observer, right? The
Yeah.
observed actions, and then the code function, the probabilistic behavior of the secret.
Yeah. We are
When
going
you
to
combine it with
externalize the
the
probabilistic behavior to the code functions. And we're going to assign a probabilistic distribution on code functions. And this probabilistic behavior of the code function is going to emulate the probabilistic behavior of the inputs themselves.
So that will be
Externalized.
externalized.
Yeah. And then that's I'm going to get there at some point. That's exactly the main theorem. That it's always possible to do this externalization. So the first thing we need to do, yes, is to go from here to the channel. So I'll leave this guy here. So we need to define who are these probabilities here of beta, of outputs, given the history of inputs and outputs. This is easy to do. The probability of an observable given the history, you just follow the path, pick the observable one, and then you have the history up to this point. The probability of this point is going to be assigned there. So for instance, you have an observable expensive here. So the probability of expensive given expensive and poor as a history is going to be this guy here. So this is the easy part, and you can always do it because the observables always have a probability assigned to them. So we can always map directly this guy into this guy. Also, we remember that, no, it's not here, oh, you see it's here. So, to model a system, we need to define the joint probability distribution. So, it's enough if you can define those two guys here. So, it's easy to do, it's what we just did, to go from the system to the channel by defining this guy. You just go to the tree and pick the probability that corresponds to this observable given the history. The problem, you can also do this with this guy here. You go to the tree, and if it's fully probabilistic, and you pick the probability of an input given the history. And then this guy maps nicely to this guy. It's direct conversion, no problem. The problem is how to represent a probabilistic behavior of inputs if the functions here are deterministic. So that's what more or less what Malakari asked. So what we are going to do, we are going to externalize this behavior here to the code functions, and then they are going to do the work for us. So how do we do that? We have here, to fully describe the behavior of the system, we need to define the joint probability of inputs and outputs. Then we are going to create here another joint probability distribution that also takes into consideration the code functions. So we're taking this guy, and this guy, and putting them all together in a new probabilistic distribution, with the restrictions that this guy needs to be compatible with what we had before. In the sense, specifically, that what the probability of a code function given the history needs to be equals the probability of the real probability of code function given the history. The probability of an input symbol given history needs to be equal what this guy says is that the choice of the input symbol needs to be a function. It needs to be exactly, it's a distribution. There's a delta of direct of the function applied to the feedback, which means that alpha needs to be deterministic. And the third condition is that the output symbol given the history needs to be the same probability assigned here. So we want to create a joint probability distribution that is compatible with the system we are modeling. And it's possible to do it. And there is only one probability distribution that does it. And our main result in the paper, I can just state it. The main result is that it's always possible, given a system, to create a joint probability distribution taking in consideration code functions that is going to be compatible with the behavior of the system. So, take any system, you can always create this joint probability here that is going to be behaving exactly like the system would be. And then, working well, because the choice of the input symbol is still deterministic, but this is being covered by the choice of the code function at the input. So, it was a very nice result when we found it, and it is specifically useful because now, if you can create this input distribution here, this joint distribution here, we can calculate the capacity of the channel, and then recover the idea of maximum leakage and information flow. So, what we do then is that this model is going to be simplified after we do this. end up with a system that's like this. We rename the code functions to reaction functions. Because here we are not dealing with communication, we are dealing, so we are not coding anything. The reaction functions are the functions that represent how the environment reacts to the protocol. It will be a representation of the users, everything that is outside the protocol. So it's represented by the reaction functions. So you have your external system providing reaction functions. Then here we have an interactor that is gonna produce symbols given a history, and then this guy, well, I'm gonna do like this. No, not really nice. Sends the produced symbol to the channel. And then it is off. And then this guy here is a black box. And that's what we have. So here we can model two different parts. We can model the protocol itself. What's inside the box depends on the protocol. It's going to be always probabilistic. What is outside depends on the environment. So if you have enough knowledge, we can attribute some probability distribution to these reaction functions here. But if you don't know what's going on outside, we will just assume it's non-deterministic, and you can use channel capacity to get the worst case leakage. So what we define a reactor as being a probability distribution on these guys here. So if we have enough knowledge about the environment, we can attribute the probability distribution to these guys and call it a reactor. So it's a model, a more precise model of the environment than just saying it's non-deterministic. So, okay, so we could model these systems into the channels, but then, like, to conclude the talk, how much time do I have?
10 minutes?
Okay, oh, this is gonna be perfect. So, what we did this, the idea to do this was to measure leakage. So, just to conclude, let's see what is leakage in this case, that we have feedback and interaction and all this. So, we know that in channels like this, the mutual information is the information that flows from inputs to outputs, plus the information that flows in the other direction via feedback. So the intuition here is that what would be leakage? So we argue that what is leakage is an attacker observes the output, and what can he infer about the inputs that generated this output? This is exactly the direct information from inputs to outputs. How information flows from outputs to inputs, exactly how the interactor reacts, it's a description of the environment, it's a description of how the world works. It doesn't belong to the protocol. So we argue that it's not really leakage. I mean, any protocol that you plug there, these guys are going to always be the same. So we would be nice to measure leakage like this. So we're going to give two reasons that we think that. First, we're going to show that when you have feedback, you can have this guy greater than 0. You have mutual information, although the direct information is 0. And all the information you have correlating the two variables are due to the feedback. So there is a very simple example. Assume that you have a channel, only two possible inputs and two possible outputs. So it's a completely noisy channel. So So no information is transmitted here. Clearly, the rows are all the same. However, we have feedback in such a way that alpha, every symbol in time t is going to be A1 if the previous symbol was B1, and A2 if the previous symbol was B2. So basically, the channel is copying every output into the new input. So we can show easily that the mutual information between A and B in this case is greater than 0. There is a correlation. The correlation is due to this guy, although there is no possible way to transmit information in this channel. So if we consider, for instance, is it as a model of a system, is it really the case that there is leakage here? By observing B, you cannot infer anything from A. So if you maximize, or if you take, even if you don't maximize, if you take mutual information as a measure of leakage, you are measuring feedback in the middle of something that is not really what it's supposed to be. So what we do is that what is the classic case? The leakage is the one information that is equal the a priori uncertainty minus the a posteriori uncertainty. So in our case, we would like to do the same in the interactive case. So what would be the leakage in a time t? So what you can learn from the sequence of secrets by observing an output, given the history of outputs, this guy is exactly the same thing for one time step. But so the amount of information that you can get from inputs, given one observation, is the difference between what you have before and you had after. The interesting thing, if you sum this guy for every t, we get exactly the directed information. So it's another justification why it seems natural to use these as a measure of information leakage. So also, equivalently, if you have a secret non-deterministic system where you don't attribute probability distributions to the inputs, we are going only to consider the capacity, and then we have a formula for capacity now. We can just use this. So to conclude, there are two things that we think that are interesting to discuss. Is that first, if in some scenario someone can consider that, okay, I agree that the feedback information is not part of the system behavior, it's part of the environment, but still it can give some information about how the secrets are being produced. They are not due to the protocol, but anyway, they give more information about how the secrets are being produced. So from the point of view of the attacker, it could be considered as a good way to know what's going on. So someone could consider that. If you can consider that, you can still use this model by considering mutual information. And it's just the same as the classic model. Also, an important observation is that the classic model works because the information from feedback, if you don't have feedback, the information, direct information from outputs to inputs is zero. So the mutual information is exactly the directed information. So you are measuring always directed information without being aware of it. So this model is an extension, it's smooth extension, which is beautiful. And as an open problem, that's the last thing, is that we did it for Shannon mutual information and the model of attacker that can ask, does the secret belong to a set? We don't know exactly how to do it for the Smith concept of renaming entropy and what would be one try attack in this. It's an interesting question that we still have to think more about how to approach it. We tried, but we found some problems that we're still working on it. So, I mean, it's a minor technical detail if someone can ask, I'll talk about it later. So, I think that concludes the talk.
Okay, thank you.
Well, a little bit of a joke, but I think that maybe if you do with Rennie's entropy these kind of things, imagine you can do maybe with lots of technical difficulties in the end. But the point is that when you take all Rennie entropies different from Shannon entropy, is that the chain rule doesn't work anymore.
Yeah.
So, and I think for all the framework of this work, the chain rule is everywhere.
Yeah,
So you
that's
may
exactly
have
the problem.
ah.
Yeah, we cannot compose the leakage in one step. It's not a composition of the leakage.
So maybe if you really want, I imagine that with lots of efforts you get a machine, but it will be such a maybe clumsy compared to this that is so elegant.
Yeah, yeah, that's exactly our problem. We tried a couple of ways to try to find some sort of compositionality that was not the chain rule, but we didn't come to anything that is elegant. I mean, we came up with something, but it's so much work that it's not even worth it to propose it as a solution.
I was just thinking, the feedback is not part of the research decided, but could be perhaps some sort of modeling the sections of negative adversary. So
Yeah.
in a sense, it would negative adversary influences the steps, moves, protocols. So that's
Yeah, yeah. An active adversary could feed exactly an output to the user,
it's
so
a
that
limited kind of active adversary that is just sense back to the observables, but with the relation understanding feedback is something more complicated.
I don't know. Maybe you can also think of an adversary, maybe that he sees the observables and he sends a different point to the user. Yeah, he fools the user,
Produces noise.
introduces noise, and try to force the user to do something.
At some point you said that some channels have...
right? So for whatever feedback you have, the leakage is the same. So whatever, if you want to model the feedback as the adversary skills to introduce some noise or to create some problems, then it's not going to show up in the leakage.
Yes, but this will use way to separate the things.
Cross-test question.
That gets
Cross-test question.
So at some point you said that some kind of channels have the same capacity as the normal ones. So was that memory without feedback, or I didn't...
If a channel doesn't have memory, let me see if it's the question you're asking. If a channel doesn't have memory, adding feedback does not make any difference in the capacity.
Yeah, that's the one case.
If the channel has memory, adding feedback can make a difference.
Ah, okay. Then for that kind of capacity, like the new one of this guy, so that I assume the rule is some kind of theorem like Shannon one, right? That formula gives the maximum rate of information that you can pass through the channel.
Yes. Yes. There is not exactly correlation. Because like in the other example that I gave here, you can have a high correlation without having any transmission of information.
Yeah, that's true. That was interesting. Yeah, no, that's a nice thing. But lots of intuitions are lost from the case.
Sorry?
No, this is a nice thing where lots of intuition is lost from the typical scenario. So yeah, things are puzzling.
I seem to remember seeing a draft of this paper some years ago. Is that will be submitted to a conference? Maybe I reviewed it there.
Concord.
Yeah, okay. So, so much for anonymity. So I remember at some time, at some point, you had some proof of continuity with respect to some metric.
Conservation metric.
Can you say something about that? What was that about exactly?
Well, it's more artistic contribution.
Can you check and say something about it?
Well, essentially, the stage the result compared with its paper 2002.
Correct.
Yeah, well, it's really the same result. The main thing is that in your case, there is this problem that both Miguel and Mario pointed out, that you cannot really consider the channel as an invariant with respect to the input. The channel is not invariant with respect to the input, and therefore you can speak of capacity, because capacity you have to maximize overall input, so if you change the input, you change the channel.
Okay, so you still get a continuity with respect to that
Yeah,
center of
in
this
this
metric.
setting where now the channel is really invariant with respect to the input distribution, you can now speak of capacity and that continuity result.
And you get some kind of contextuality property also? Or just you haven't really defined it?
Contextual what?
So we prove this thing that if you put things in a context that decreases the distances,
Yeah, we don't have.
you don't have a notion of context and
Yeah, no,
plugging.
we don't have a language.
Right. Okay, good
The
thing.
metric is really the same in the systems.
Well,
Well, this automata provide the language, right? So you could,
Right and language.
I mean, well, at the opposite, you could have a simple language that provides this kind of automata.
Sure. Could define a language on top of it, yeah. And so that it would be really the same result as percussion. The main thing, the thing that we have changed is only the part of the channel. This system, this automata is the same. So in the Fedorovich metric over the automata, it's the same definition as the one in percussion.
and Hatter. And many other people. Well, anyway, thanks a lot.